We'll now talk about R squared and adjusted R squared as a possible way to choose among models. So R squared, we remember, is the percentage of variation explained by the regression model. And it's defined as the sums of squares regression divided by the sums of squares total. And the interpretation of percentage of variation explained comes from the fact that when you divide the sums of squares by n minus p plus 1, in both cases, this is the estimated variation, right? But the denominator cancels out, so we can just talk about sums of squares. Okay, so here we have the model, actually the Bush model, Bush election model we talked about before. And each row corresponds to a model. The number of variables in the model is given by k in front here. And for a given k, we list the best two models. So the best two one variable models are in the first two rows. And there is one model that has income and the other model has votes change. The criterion is here listed at the end. We're listing R squared. And so we have 14.8% and 17.8%. Now, R squared is unfortunate as a criterion because as you add a variable to a model, it explains additional sums of squares. And sums of squares are positive, of course. So if you have a model and add a variable, regardless of what the variable is, sums of squares go up. Well, theoretically, it could, in very strange cases, it could not go up but add 0. But basically, it goes up. And that makes this criterion not very suitable for model selection because you always end up deciding, if you use this criterion, that the model that has all the variables in there is best because it has the highest value of R squared. And that, of course, is not really our goal, right? To put them all in there. Okay. This just says the same thing. We are developing now another criterion, the adjusted R squared. And the idea is to look at what model leads to the smallest mean squared error, where the mean squared error is defined as usual, sums of squares error, right, or square of the residuals here directly, divided by n minus p plus 1, the degrees of freedom. So that is the model that minimizes MSE is the same model that maximizes the adjusted R squared. Why? Because the sigma squared of the null model, y equals beta 0, is constant. 1 is constant. So if I minimize this, then 1 minus something that I minimize is maximized. Okay. So I now have a new criterion, R squared. And for the null model, we can express the sigma squared in terms of the total sums of squares. Because for the null model, y equals beta 0, the predicted value is just the average y, because predicted beta is the average y. And then the sums of squares error are actually the total sums of squares. That only works for the null model. So with that realization, I can rework the definition by putting in the sums of squares error for both models here, but then substituting sums of squares error with sums of squares total for the null model. And because sums of squares error divided by sums of squares total is just 1 minus R squared, we can actually arrive at a formula of the adjusted R squared that is a function of R squared. That's kind of cute. So the adjusted R squared does not necessarily increase as you add another variable. And choosing a model based on the largest adjusted R squared will choose the exact same model that you would choose by minimizing the mean squared error. Here's the same table as before, same variables, but now I have the criterion is adjusted R squared. Well, when I say the same table, I mean the same setup. The best two models are now not necessarily the best two models that we had before, right? Because we have a different criteria. So we're maximizing adjusted R squared. And I have the question for you. Which model maximizes my criterion? And I will leave you to answer this and march on. And I'm not marching a lot because here I have some R code for the previous output just for completeness. All right, this ends this segment.